Hey folks, Mrs. White here with our day 2 of lessons that you're going to be seeing this week. So hopefully the material that was released on Monday, section 5.1, went well for you. If you needed help on it and did not reach out, then please send me an email. We can do our own appointment through Zoom to make sure that you're good to go. Just let me know where you're at, okay? Um, if you have not turned in the homework, I know that it was due by midnight last night, then please email me with it. Okay, I'll give you till the end of business today if you can attach it on the classroom. I also want you to take a second and check Power School. I did update grades since I've been away, and everything's there. So pretty much your quarter 3 is done right now. These homework assignments are ungraded at the moment, and so your grade is pretty static. Okay, it ends in 2 weeks on April 3rd. You know at this point that is clearly not 2 weeks. It is like a couple days. Okay, so please, give yourself an idea of what's going on for your quarter 3 grade. Today, we're going to move on in our book to section 5.2, which is composition of functions. And I've been calling plugging in a function into another function composition of functions back from chapter 4 because it is composition of functions of sorts. Okay, it's more like computing with functions. Today, we're going to really talk about what is composition. So, what is the definition of a composition of functions? How do we write it with symbols? Because there's actually specific symbols for it. How can we evaluate it? Okay, which is a little different than simplifying somewhat. Okay, how can we evaluate it? How can we find if two functions are compositions of each other? And then when would this be used in the real life? How can we apply it? So I'm going to try to do what I did last time, which is focus on the mathy stuff, and then do at least one example, depending on how long this lesson is, of how we could apply it. Your homework is this worksheet. I'm going to link it underneath the video. I do not want you to do the whole sheet. I will also link a screenshot to the answers, okay? You do not go to my homework page. It should be right on Google Classroom. But again, you're not going to do the whole sheet. At the end of this lesson, I'll talk to you about which items you should do, okay? So if you haven't already, make sure you do hand in that homework. Check out your Power School. And then we're going to get started right on 5.2. So we're going to start off. Make sure you have a notebook out. If you don't have it, feel free to take a second and grab one. Again, this is section 5.2 in your book, and we're looking at composition of functions. And like in the last unit, I do want to kind of really look at some mathy language as far as definitions. So I took a screenshot from the book again because I think this is one that we really could unpack together and it could make some sense. So suppose f and g are functions. So it'd be like f of x and g of x. Okay, they're functions such that the range of g, so that means instead of range, we could say the y values, such that the y values of g are a subset of the domain of f. And domain, again, goes with our x's. Okay, so let's read that again. Suppose f and g are functions such that the y values of g are a subset, or they're within the domain of f. So the x values of our f. Then the composition function f, and then this funky little dot, which we say of, okay, f of g can be described by f of g of x or f of g of x, which you would say the same way. These two things are synonymous. Now we've been doing this, right, where we took a function, we plugged it into f. The new notation is this, along with this actual piece that, yes, it does work or no, it doesn't work, okay? And this little open dot is how we read it. Because we're essentially plugging g of x into f, right? And if we're plugging g of x into this, really we're plugging the outcome of that, right? The outcome of g of x, which would be the y's, into the f values for our f of x. And that's really what it's telling us to do. We could also kind of see this with this little flowchart. So if we take our domain of g, okay, so we have our g, we're going to plug in our domain for it. Okay, we're going to plug in the x. That's going to give us g of x, right? When we solve this, we're going to get the range of g, right? We're going to solve that out. Then, in order for it to be a composition of functions, that answer has to be in the domain of f, okay? So that means we're going to have to plug that in as our domain or as our x values into the f function. And that is how it's the same thing as this. Now, I know it feels weird. Big idea is that you should have this down. I do want you to write that the range of g is a subset of the f domain or the f x values, okay, because that's going to come into play in a little bit. So let's look at evaluating these a little bit using constants, okay? So how and what the heck does this even mean to us in Algebra 2? So f of x equals x squared minus 4, and g of x equals 2x plus 1. It's saying find each value. Now, it's not a plus, it's not a minus, it's not a multiply, it's not a divide. This is our composition symbol, okay? We would read this as f of g of 3. So we could start off by thinking about rewriting this, okay? We're not going to plug in 3 into our f and 3 into our g and then do whatever with this. If we look back at our actual definition, okay, we're going to take whatever that value is, we're going to plug it into g, solve it, and then plug that into the f, okay? So, we're going to take this, we're going to start by kind of rewriting it as f of g of 3, okay, which means we're going to plug the 3 in for g and solve, and then plug that into the f. So I'm going to take my g function, 2x plus 1, and I'm going to rewrite it with my 3 in there. So I'm going to do g of 3, which equals 2 times 3 plus 1. I'm sure you guys have already solved that. 2 times 3 is 6, plus 1 is 7. So g of 3 equals 7. So up here, if I think about it, right, if g of 3 equals 7, I could just find f of 7. And that's not too bad. Okay, I'm going to come to my f function. I'm going to plug in 7. So to do f of 7, I'm going to have 7 squared minus 4. 7 squared is 49. 49 minus 4 is 45. So I get that f of g of 3 equals 45. And this is my answer. Okay, f of g of 3 equals 45. So let's do this one together. We'll do 2, and then I'll have you try 2 on your own, and you can check your solutions. Okay? So I see another one. In fact, if we look, f of g of 3, this one is g of f of 3. And you might feel like, well, aren't these going to be the same, Mrs. White? It has the f and the g, and it has a 3. Well, let's find out. Okay? First off, we want to rewrite this in a way that's going to make sense. We're going to have our g function, and we're going to be plugging in f of 3. Well, f of 3 is just a number. I'm going to find f of 3 by taking my f function. I'm going to come over here, and I'm going to plug in 3 for my x. So instead of x squared, I'm going to have 3 squared and then a minus 4. Well, 3 squared is 9, and 9 minus 4 is 5. So I could say that f of 3 equals 5, or at this point, I'm going to calculate g of 5. Okay? So to get g of 5, I'm going to come over to my g function right here. I'm going to take out my x, and I'm going to plug in 5. So I'm going to have 2 times 5 plus 1. Well, 2 times 5 is 10. 10 plus 1 is 11. Now, g of 5 equals 11. I get that. But at this point, when we did g of 5, we actually found g of f of 3, which is the same thing as g of f of 3. So I'm ready to write my answer. G of f of 3 equals 11. So my question to you is now, if we do f of g, if we do g of f, do we end up getting the same answers? And it's obvious the answer is no here, okay? That we do not get the same answers if we flip-flop the composition. We get totally different solutions. So keep that in mind, okay? If you flip-flop them, it's not the same. So I want you to take a second. We have 2 different functions down here. Pause the video, okay? And give it a go. All right, I'm going to solve them out silently and quickly, check my answers, and then we'll move on. Okay, so if you need to, pause it, look at my work, and see if you made a mistake. So if you need to, again, look through this work. I've put it up for you. I'm going to move forward to our next thing that has to do with composition of functions, which is a little bit trickier than this. So here's where it gets a little hairy. It's when we're dealing with equations that we're plugging in where they don't give us a value, okay? Or relations. And remember, a relation is a set of coordinate pairs. So I rewrote kind of this definition, or I took it from the book again in a little bit of a different way so that we can keep it and reference it as we're trying to look at these problems. So the composition of two functions may not exist, okay? So if we look back at our definition, oops, maybe we won't be able to look at it, okay? The range has to be in the domain of our f. So the outcome of g, its y values, okay? The outcome have to be in a subset of the x values for our f. So that's going to be what changes things here, okay? It's not going to be able to be a composition of functions unless that's actually true. So given two functions f and g, f of g of x is defined only if the range of g of x is a subset of the domain of f, okay? So the y values in our g have to be within our x values of our f. Likewise, if we do the opposite, you have to have the range of f of x, right? Because that's the second number. It's always the second one. The range of this has to be within the domain of this. So it doesn't always have to be the f or the g. It's whichever is listed second. The range of that, the y values, the outcome have to fit within the domain of the original. Okay? So if we look at our first example here, my definition starts out by looking at this second piece. So it asks me to find f of g of x and g of f of x for each if they exist. So let's start by trying to find f of g of x and seeing if it exists. Okay? So in order for it to exist, all of the ranges, okay, all my y values in my g function, okay, have to be subsets of my f function domains. Okay, so all my y's here. So if I'm thinking of my g values, okay, so I'm going to start off by thinking of my first coordinate pair here. So let's come here. My g of 8, so I'm just taking that first x value right here. My g of 8, if I plug that in and do whatever I need to, my output is my y. It's going to be 15. Okay. I'm going to take that 15 now and I'm going to look for it. This y value must be a domain value or an x value in my f. So I'm going to look all through these. This y value of 15 does exist here. So if I were to take that 15 and plug it into my f function as an x value, it does work. I would get 11. Okay, so far I'm feeling like this is good to go. It could potentially exist. Okay. And so this would be part of my coordinate pair, okay? Remembering that what I initially plugged in was 8. So this is going to seem tricky in the first one, but we'll get it on the next ones. My coordinate pair for f of g of x would be that I originally plugged in 8. I got an answer for my range here. I plugged my range into my x here. I got out another y value from my x, or from my f, and that's my y. So this coordinate pair is the resultant of plugging this in and figuring out what happened over here. Okay? So let's do the next coordinate pair. We have to do the same process with all of them. So I look at my g's first because I need to find the, check out what's going on with my ranges and my domains. So I'm going to come over here. I'm going to take my x value. I'm going to do g of x first. So I'm going to do g of this x value, which is 5. Okay. Now g of 5, if that's the x, the y value is going to have to be 1. I'm going to look, is 1 an x value in my f function? So if I look over here, oh yeah, it's right there. Okay. So that means if I take this and plug it in, which is what I would normally do, right? Solve for g, plug it into the other one. If I take this, f of 1, my outcome for that would be 8. So my coordinate pair, oops, not that part. My coordinate pair is going to be the original x I plugged in, which was 5, and the new y value from my other function, which is 8. Let's check our third coordinate pair. Okay, so I'm going to look at this one. I'm going to plug in, because it's g of x, my x value, which is 10, g of 10. And I would get out 14. Again, that 14 is just coming from this coordinate pair. That's my y. That's my outcome. Okay. Now, in order for this to work, it has to have an f with a 14 in it. So if I look over here, I do have a 14. It is equal to 9. That means my coordinate pair is whatever I originally plugged in, 10 and 9. One left. Okay. I'm going to check this one out. So I'm going to have g of 9 equals 0. I'm going to see if there is an f of 0, and there is. Here's my x value for 0. That's going to equal 13. So my coordinate pair is 9, 13. So right now, because all of the ranges, okay, all of my outcomes for my g's were domains for my f's, I do have a composition of functions. My f of g of x would be, in curly brackets, all of these coordinate pairs separated by commas and ended with another curly bracket. Okay, if you want to take a second to write that down, f of g of x would be these 4 coordinate pairs in curly brackets. All right, so now we're going to find, because if we look back at our directions, it says g of f of x. So let's look. G of f of x. Okay, so it's not a multiplication, it's the of. Okay, because f is listed second, we're going to look at our ranges of our f and see if they're in the domains or the x values of our g. So we're going to start off with all of our f coordinate pairs. So we have 1, 8. So we're going to plug in 1. We're going to get out 8. And we're going to see, yes, there is an 8, right? Our outcome, our y, is an x value in our other function. So if we were to do g of 8, we do get an answer. It's 15, the other half of that coordinate pair. So our composition coordinate pair, right, if we plug in a 1 and get out the other, would be 115. Let's look at our second coordinate pair. We would have f of 0 equals 13. So I'm going to look into my g function. I'm going to look for a number 13 up there. So there is not a 13. Now what this means is that this coordinate pair is not possible. Not that there's no composition entirely, just that this one piece does not exist. Okay. This does as part of the composition. There could be potentially 2 others that work, so we'll have to check each of those. So next we would have f of 15 equals 11. We're going to plug into 11 into our g function, and we're going to see what happens there. So 11, there is no 11 in our x's, right? We're looking here, 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 or here. There are no 11s, so this one also does not exist. Let's take a look at our last one. It is going to be f of 14, and that's going to give us 9. Again, I'm looking at just my last coordinate pair here. Does g of 9 exist? It does, and its outcome is 0, so this is good, okay? I'm going to end up with 14, 0 as my other coordinate pair. So that means this composition of functions actually only has 2 coordinate pairs, okay? Because this one and this one were not possible. So we do our curly brackets, 1, 15, and 14, 0. So that's our relation. Now, I want to remind you, if we were to do the domain and range of each of these, our domain is a list of all of our x values from least to greatest with no repeats. So here I would write domain, colon, curly bracket, 5, 8, 9, 10. My range for this first one would be all of my y's in order from least to greatest with no repeats. So 8, 9, 11, 13, all separated by commas. Okay, because this was discrete, meaning it's just points, it's not something continuous, it's not an equation, I write my domain and range like that. And here my domain would just be 1, 14, and my range would be 0, 15. Okay? Now that's all well and good with coordinate pairs. That actually is a lot of work to find the compositions, but it gets a little bit trickier when we start looking at equations, okay? So let's take a second, write these 2 equations or these 2 functions down. We have f of x equals 2x minus 5, and g of x equals 4x. And it has the same set of directions. It's asking us to do f of g of x and g of f of x to see if they exist. So let's write down the first one. F of g of x. So what this is telling me is take my f function, plug into my f function my g of x. Okay, they did not give me a number for x. I'm keeping it as x. This, folks, even though this looks different, is something that we actually have practiced before. We just didn't double check if they were compositions. So I'm going to take my g of x function, which is 4x. Okay, that's what g of x equals, and I'm going to plug that into f of x. So I'm going to do f of 4x, essentially. So I'm going to come to my f function. Everywhere that an x happens, I'm going to plug in 4x. Okay, so I'm going to plug in my 4x here. Love that green. Okay, so we're going to write it as 2 instead of x. We're going to plug in the 4x. Close that up, and then we have a minus 5. And this is equivalent to, well, 2 times 4x is 8x minus 5. Okay, so we could say f of g of x equals 8x minus 5. Now, if we're relating our domains and our ranges for this, okay, we need to look and think about each of these pieces, and then if this would be within it, okay? So I'm going to think of my g, okay, of x, this. Hopefully, when you look at this, folks, you notice your x is to the first power, so this is going to be a line. If we think of the exact line, it would start at 0, 0, go up 4 forwards 1, down 4 backwards 1. It'd be a positive slope. So what is the domain and range for a line? It's all reals, right? It goes forever to positive, forever to negative, forever to positive, forever to negative, right? If our line's going like that. So all reals for both. That means every number, specifically for our range, right? Because we care about our range of this, okay, has to be included within our domain for this. So look at this one. This is a line, okay? So our domain for this one, it would start at negative 5 and go up 2 forwards 1, up, down 2 backwards 1. Okay, it's going to be another positive slope like this, is also all reals. So is all reals contained in the domain of all reals? Heck yeah, it is. That means that this works, okay? Let's look at our other problem. Let's say we're doing g of f of x. And remember, that's taking our g and plugging in our f of x into it, okay? So it's kind of like taking g and plugging in 2x minus 5. Again, because f of x is 2x minus 5. So we could rewrite it. Instead of 4x for our g function, I'm going to put 4. But again, instead of x, we're plugging in 2x minus 5. Okay. I would distribute that through. Boop, boop. 4, oops, just kidding, 8x minus 20, okay, is our g of f of x. So you want to think back to this, okay? So now instead of starting with this one, right, we're starting with our f instead of our g. So I want to think of what is my range for this one. So my range here was all reals. And I'm plugging my range, again, I knew it was all reals because it was a line. I'm plugging my range into my domain here. So does my domain here include all reals? Well, yeah, this was a line also, okay? So since all reals fits into all reals, we're good to go, all right? This one also is a composition. It works perfect. Here are a couple additional problems. If you want to give those a go, you can. Feel free to pause the video. So folks, hopefully looking at this first one, if you gave it a go on your own, you notice that our f of g of x is 3 coordinate pairs because one of them did not exist. and you should list those in curly brackets. G of f of x, if we were to do the opposite one, okay, is going to be undefined. Now it's undefined because every time I took these coordinate pairs and I looked at each of the y values, not one of these y's existed in the domain or the x values of my g function, okay? None of them worked, so a composition of functions also will not work. Take a second, solve this one. I'll do it silently, and then we'll discuss. So instead of x squared, I'm going to put x minus 6 squared plus 2. Now I'm going to solve this out. So right now, folks, this is f of g of x, okay? And we need to check our domains and our ranges. So our outcomes of this, okay, our range of this must be contained in our domain of this. So we have to think our range and what type of graph this is. So it's an exponent of 1, that means it's a line. That means our range and our domain both are all reals. So now we're going to make sure all of those numbers exist in the domain here. So what is the domain for something to the squared power? You should be familiar with that, folks. Anything to the second power, if that's our degree, is going to be a parabola, right? It's going to look like this. Or it's going to be frowning and look like this. So if it's smiling, okay, and we're talking about the domain as we come out this way and come out this way to positive and negative infinity, it's continuing on, right? It's going up, but it's also going out, and over here it'd be going up, but it's also going out. So our domain is also all reals. So will all reals fit inside all reals? Yes, this one works. We would say f of g of x equals x squared minus 12x plus 38. Now I'm going to do the other one up, and we'll talk about that one. So to do this now, I'm going to take my g function here, and I'm going to plug in, instead of x, I'm going to put x squared plus 2. So here's my answer right now. I have g of f of x equals x squared minus 4. So in order to make sure that this composition actually does work, which is kind of our new learning here, I take my range of my f functions, so my range here, okay, and I'm going to ask myself, is it in my domain here? So my range here is going to be, if I think about this graph, it's a parabola and it's shifted up 2 places and it's smiling, so it's going to be like this. So my range, my y values are going to be that anything that my y's are going to be greater than or equal to 2. Here, this is a line, so my domain and range are both all reals. So are all the numbers that are bigger than 2 included in all reals? Yes, it is. So that means that yes, this composition of function works, okay? We have to kind of know some stuff about what the graphs of these are and what the domains and ranges of each of those are to make sure that they actually do work, okay? Alrighty then. Let's keep going, okay? So the last example we're going to look at is going to be how can we use function notation to kind of help us out as we are trying to solve real world problems. So take a second, read this over. A new car dealer is discounting all new cars by 12%. At the same time, the manufacturer is offering this rebate on all new cars. Mr. Navarro is going to buy a car that's priced at $24,500. Will the final price be lower if the discount is applied before the rebate or if the rebate is applied after the discount? So how is he going to save the most money? So let's think about an equation, kind of keeping this out of it for now, okay? Let's come out with an equation that's going to have our original price discounted first, and then the actual like rebate on the car. So let's do a function for the discount, and we'll use x being the price of the car. We know our x is going to be this eventually. If we're doing a discount of a price, we're going to take the original price, and you're going to subtract from it 12%. So I want you thinking back. We did just talk about this in section 5.1. We aren't adding 12% to it, we're subtracting it off. So we really aren't going to do 1.12. We're just going to change this to a decimal, okay? And we're going to find 12% of that original price, or we're going to do 0.12x, okay? So that's going to give us just 12% of the price. We're going to subtract that then from our original price. The other function we could potentially be working with is our rebate function, okay? So if we're doing a rebate from the price, then it's just going to be our price minus $1,500. So we've found one for an equation for the discount, an equation for the rebate. We did not combine the two, okay? That's where composition of functions is going to come in. We could do d of r of x, okay? And what that's going to do is that's going to first, if we do d of r of x, that's going to be the rebate is going to be given before the discount, right? Because we'd have d of r of x, which means we would solve the rebate first and then plug it into the discount. So this is rebate and then discount. We could do the exact opposite, right? R of d of x, where we're going to have our rebate happen second because we're doing our discount off the original price first, right? Discount off the original and then plugged into the rebate equation. So let's see which of those two compositions of functions works better. And this might not be your initial strategy, but it's a way that we could really utilize composition of functions. So we're going to take our r of x, x minus 1,500, and we're going to plug it into our d function. So that means we're going to take this x minus 1,500, and we're going to plug it in everywhere that x happens in our d function. So dx 1,500 equals x minus 1,500 minus 0.12 of x minus 1,500, okay? And we could choose to either simplify this or actually take a second and plug in the real price, okay? So let's plug in our 24,500. Maybe we do that first, okay? So 500 and 500. 24 minus 1 is going to be 23. So we're really plugging in this instance, if we do the rebate first, we're plugging in 23,000 here and here. So we're left with 23,000 minus 0.12 times 23,000. And this product here, folks, if you grab a calculator real quick, okay, if you were to multiply those two things together right now, that's going to be your actual discount. Okay, how much that 12% is going to be off. And if we subtract the two, we end up getting 23,000. Sorry, I'm like, why am I off a little bit? That's not a very expensive car. That's much better. We end up seeing that our discount right here, if you multiply those two together, is 2,760. So if we do our 23,000 minus the discount here, our 12% off, we end up with a car that costs 20,240. Okay, and remember that is our D of R, which means we do our rebate first and our percent off second. If we do kind of the inverse of that, okay, that means we're doing R of D of X. So we're going to take our R function, we're going to plug in D of X everywhere that the R occur, or everywhere that X occurs in the R. So our D of X is equal to X minus 0.12X. Okay. So we'll write that over here. Let's actually solve that right now, right? Let's get that number to something a little bit more digestible. So we're going to take our 24,500, 24,500, 24,500. We're going to solve that out. So let's see, this one's going to be just the 2450. 0.12 times 24,500 is going to be 2,940. So we're going to take this number and subtract that from it. So we're really not doing anything but R of 21,600 560, excuse me, 560. So again, if you're typing this all in your calculator, do 0.12 times this, you get your 2,940. You do 24,500 minus this, we end up with this. Now we're going to take this value and plug it into our R function. So we're going to have 21,560, and we're going to minus 1,500 from that. So minus the 1, minus the 5 here, we're going to end up with this as our total price, okay? And that's how much the car would cost if we do our discount first, our percent off first, and our rebate second. So if we look, clearly they're not the same. Which one would Mr. Navarro want to do? Well, heck yeah, he wants to do this one. He wants to do the percent off and then the rebate. And $200 might not seem like a lot to you, but over the course of a loan, that $200 could be worth more, okay? That could be like a month off of payments at least. So let's just revisit what we did in this problem so that when you attempt the word problem, because you're only going to have one, the word problem on tonight's homework, you know how to tackle it. So first things first, you're going to read the problem. They're probably going to give you a number to plug in, but I want you to pause on that, okay? I want you to think what are they asking you to do? So you're going to write one equation for each of the items. So in this case, it was the rebate from the original price and the discount from the original price. And then you're going to model it as two separate compositions of functions to see which one is a better deal or not. So if we look at your homework, I pulled up a screenshot of it here. This is the sheet I want you to be doing. I want you to do number 1 and number 3, so 2 of the coordinate pair ones. I want you to try number 5 and number 8, okay? So that's looking at doing compositions for G of H, and H of G. Okay, you're still doing 2 for each of these, but it's dealing with equations. So you have to think of what does the domain and range of each of these look like. Then coming down here, if you look, you're actually plugging in constants, so your answer should be in constants. So you're not going to have to worry about it coordinate pairs. You're not going to have to worry about it being an equation. The answers for 11, 14, 17, 20, and 23 should all be just a number. Okay, and then I do want you to take a look at 26. It's a little bit easier because they wrote out what the functions would be. They just want you to do a composition of functions with it. Okay, so quick refresher: 1, 3, 5, 8, 11, 14, 17, 20, 23, and 26. So right down the left-hand side. I am going to attach the key because I want you to know if you're doing it right or wrong. So what that means is when you show me that you have completed these problems, you are most definitely showing work for all of them. Okay, even if it's just lines, maybe you figured out a different strategy to start solving those a little bit quicker, okay? But you're definitely showing work for each of these problems right here. Again, if any of this is tricky, and composition of functions is kind of weird, especially with domains and ranges, show up to my office hours, okay? It's going to be on Friday, same time, same place, and if you need questions answered, let's make it happen, okay? Talk to you folks then. Bye.